Thank you for your joining to the lecture. The subject of our video lecture is a new decision support model in the sustainable operation of large-scale irrigation systems. This program distributes water at the network level in three main stages. Distribution of water from the main canal to the secondary canal, distribution from secondaries to tertiaries, and water distribution at plot level. In the program, the entire network is divided into different segments. The main canal section between the points where two consecutive secondaries receive water, a primary level segment. Here we can see on the chart. Secondary canal section between the points where two consecutive tertiaries receive water, a secondary canal segment. And the tertiary canal section between the points where two consecutive plots receive water also forms a third level segment. So we can divide the entire irrigation network to different segments in accordance with their level. Also, four main components are defined for each segment in the program. The first, inflow to the segment. Also, this is a trapezoidal open canal segment. The second, water conveyance loss along the segment. The third one, amount of water received from the segment for irrigation applications. And the fourth one, outflow at the end of the segment. So we can see the properties of water flow in an open canal segment. Here we can see also different segments of the irrigation water network. In the system where the research is carried out, water is taken to the plots, parcels from the tertiary canals. Therefore, the planning process in tertiary canals will be described in detail to reflect the impact of water distribution programs at both secondary canals and the parcel levels. Planning processes at another levels were carried out in a similar way. Main modules included in the program is the first one, structural module. This module contains water carrying capacity of each secondary canal segment, canal length, segment length, inflow to the secondary segment, water conveyance efficiency as a percentage of the inflow to the cross section for a given canal length. The other one, size of the area irrigated by each tertiary canal. Maximum water carrying capacity of tertiary canal is the last component of this module. Yes, there are points in the network where water is taken directly to the plots from the main or secondary canals. These types of plots are also defined within the program and included in the planning. Secondary canal capacity is not sufficient to allocate water to all tertiaries at the same time. So, rotation planning is mandatory to operate the network at maximum capacity. Here we can see the operating of the canals with maximum capacity in the right side view. Here we can see a sample interface form with the main components in the program. Here in the first line, registration number, and below it a sample interface form in which the features of each tertiary canal and segment in the network are defined. In the right side, parameters of water conveyance efficiency and the distance the discharge conveyed from a definite segment in the network to the head of the consecutive segment, and command buttons that enable the operation of the program. The second main module in the program enables the definition of canal rotation groups at the network level. This solution is used for carry out this process. Here we can see the equations which are run by the program. In the third module, it determines the boundaries of the most suitable allocation zones in the system, their number and area size. And also, the program runs the formula given here. In the fourth module, during the system rotation period, the length of the distribution periods is determined so that an equal amount of water is delivered to the unit area of each different allocation zone. Regardless of the location of a parcel or plot within the network, the capacity of the canal from which it receives water, and the water conveyance efficiency, this parcel must benefit from the water source and the system in a fair manner, temporally and spatially. This is an important point of equity in using the system and the natural resources. This process is defined for each canal rotation group, which cannot receive water from the network simultaneously. The length of irrigation periods to be allocated to different distribution zones in a certain period is determined in four main stages. In the first stage, ratio coefficient values are defined at a specific rotation period for each allocation zone. The value of the ratio coefficient is formulated as follows. Also, the program runs the equation given here. In the second stage, system factor is determined for a certain rotation period. Also, this formula is used in the second stage of the program. In the third stage, the length of irrigation time allocated to each distribution zone in a certain rotation period is determined. Here we can see the equation. In the fourth stage, by transforming all the calculations performed in the previous stage into a general equation, the formula presented below was obtained. And also, a program is run this equation with its interface forms. In the fifth main module of the program, irrigation programs are created for a certain period of time for the plants grown in the area served by each tertiary canal. Some of the main parameters included in this module are parameters for spatial definition of the allocation zone. It is divided in 3 subgroups. Here we can see allocation zone index values in order from the upstream part of the network to the downstream. The second sub-item, the name and index values of the starting and ending tertiaries within the borders of each allocation zone. The third one, segment index values within the allocation zone. The other parameter of the module, start date of a particular irrigation application in the network. The other one, length of system rotation period. The fourth item is that the parcels irrigated by each tertiary canal within the allocation zones and the plant pattern grown there, each parcel is described in a sequence from the beginning to the end of the tertiary canal. And the fifth item, irrigation water requirements of crops at different growing stages. The other one, irrigation efficiency values for the area. The next one, length of maximum irrigation time allocated to tertiary. Next one, the maximum amount of water the canal can receive during this period. And the other one, total irrigation water requirement at tertiary canal level. And the last one is the water constraint level, which occurred during a definite period. In the sixth module, by making the desired change in the values of the parameters in the program, real-time alternative irrigation programs can be created at the entire network level. By running this module, by changing the length of the system rotation period, water constraint levels in each tertiary canal can be determined. Then, taking into account the constraints in the entire network, the most appropriate length of rotation period for the system is decided. The required canal capacities to completely meet the need for the most suitable area sizes that can be irrigated with the existing infrastructure can be determined by operating this module. With the help of this module, it can be decided to what extent and priority maintenance, repair, and renewal work will be carried out in the system. Thus, the decision maker is provided with the opportunity to foresee the optimum use of limited labor force and financial resources. The next one, in this process, before a decision is made on the operation of the network, the results of the considered operation plans can be evaluated previously by running the program and generating alternative solutions. In the 7th module, detailed report files are created for each alternative solution, and these are presented to the decision maker in the form of charts. Thus, a versatile evaluation opportunity is provided about the whole system. And here we can see an interface form of this module. When we apply this model on the research area, we can see the results. The research was carried out on 28 tertiary canals and the area they serve in the section 7, which is located within the Gediz Basin Ahmetli Regulator right bank irrigation system, for which the Gediz Irrigation Association is responsible. Here we have some views on the research area irrigation network. If we look the model flowchart, structural and hydraulic features of the network is one part. Identification of parcels in the system, efficiency values of the research area, design of canal rotation system, and identification of water distribution zones, network level irrigation scheduling for a definite system rotation period, water constraint levels in tertiary canals, and here a decision is given here. Detailed solution reports for the decision maker, and the program completes its working. There were significant differences between the water distribution plan actually implemented in the research area and the irrigation program, canal rotation groups, and allocation zones obtained according to the model. In other words, it has been determined that the actually implemented water distribution plan differs from the optimum irrigation conditions. The main differences between the model solution and real irrigation applications are as follows. Differences in drip irrigation programs at the network level, canal rotation groups, and the creations of allocation zones. Differences in system rotation period. Differences in the compatibility of irrigation applications with the existing plant pattern and the hydraulic properties of the canals. Differences in ensuring temporal and spatial acuity in utilizing the network and scarce resources. Differences in the amount of irrigation water delivered, the length of the irrigation period, and the equitable temporal and spatial use of the network by many farmers. And here we can see the allocation zones, canal rotation groups, and total irrigated area size formed by running the model for each for the research area. And we have 3 allocation zones here and tertiary rotation groups in accordance with the maximum use of the system. And total irrigated area decreases from upstream to downstream. Since the maximum water carrying capacity of the secondary canal is not sufficient to deliver water to all tertiaries at the same time, 3 different allocation zones were occurred in the research area. Since the secondary canal capacity decreases as we move from upstream to downstream, the number of tertiary canals supplying water to allocation zone 1, allocation zone 2, and allocation zone 3, respectively, also decreased. Water constraint levels occurring in alternative rotation periods for irrigation applications starting on June 12. In the first column contains the tertiary canal names. The second column contains the total irrigation water requirement in the command area of the tertiaries. Water constraint levels occurring during alternative system rotation periods is the other part. Here we can see the alternative system rotation periods: 7 days, 10 days, 11 days, and 13 days. 10, 11, and 13 days. And also the table continues, and the constraint levels program reports all the constraint levels for each tertiary canal for alternative system rotation periods. In the irrigation applications that started on June 12, during the 12-day system rotation period, a water constraint of 27.37% occurred only in the P7 tertiary, while a constraint of 7.09% and 11.72% occurred in the P9 and P26 tertiaries, respectively. The amount of irrigation water required in the other 25 tertiary canals has been fully met. Also, water constraint levels occurring in alternative rotation periods for irrigation applications starting on July 17 can be seen in the table below. Also, 7 days, 10 days, 11, and 12 days alternative rotation periods can be seen this chart. Also, this table is obtained for all the tertiary canals here for the July 17 irrigation application, for the July 17 irrigation application. In the irrigation applications that started on July 17, which is within the peak period during the 12-day system rotation period, a water constraint of 42.10% occurred in P7 tertiary, while a constraint of 19.11% and 15.20% occurred in the P9 and P26 tertiaries, respectively. Also, the other tertiaries water requirements are completely met. And also for August 10, the alternative solutions are obtained by using the modules running the program. Here we can see. For all the tertiaries, also completely different irrigation programs are obtained from alternative solutions. Yes, in the irrigation applications that started on August 10 during the 12-day system rotation period, a water constraint of 35.92% occurred in the P7 tertiary, while a constraint of 12.44% and 6.82% occurred in the P9 and P26 tertiaries, respectively. The amount of irrigation water required in other tertiaries has been fully met. The results show that a 12-day system rotation period is suitable for the irrigation network that constitutes the research area. So, most of the existing irrigation systems in Turkey consist of open canal networks. Transforming this structure into a pipe system at once does not seem possible in the short term, both economically and in terms of time, given the conditions of our country. On the other hand, the use of water for agricultural production continues unabated. Therefore, it is vital to implement scientific methods as soon as possible, which allow the most effective use of limited resources under current conditions. Thus, it will be possible to obtain maximum efficiency and income from the unit amount of constrained resources. Thank you for joining the lecture.